wants to share that. So let's start out with, I do class a little bit similar to her, and I do a lot of clicker questions. I ask you all to work together, and we're going to start out with a series of clicker questions here. I'm going to ask you to answer the question on your own, just your gut instinct, and then we're going to talk through it. You can discuss with your neighbor after you submit your gut instinct. So go ahead and answer the first question, and I want you to try to think about why you might justify your answer. So I'll wait for another 30 seconds or so. So if you haven't already, turn to your neighbor and see if they answer the same one as you, and see if you can come up with a rationale for why you would answer the way you did. Does this work when Miss Kattoum does it? Okay, so maybe she has done this before, but what I want is I want this class to get very loud when you're talking about class concepts. When I want you to come back together, I'll raise my hand. She might have done this once or twice, but when I raise my hand, if you see me raising your hand, go ahead and raise your hand, and then we'll stop talking. And so don't worry about listening for my voice. You won't hear my voice. I'm not going to raise my voice over yours, but as soon as I raise my hand, if you raise yours, people facing the back of the room will hear it, and they will join us, and hopefully we won't hear too many of those text messages during class as well. Can I have someone share why you might have answered the way you did for this question? What would you rather put your hand to? And you can share what your group discussed. So we're going to kind of take turns. I want to hear from multiple voices today, so if you usually don't talk in class, but you feel you want to share an answer, please feel free to. So can we get a volunteer? Yeah, with the student second.
I put C just because neither one of them sound like a lot of fun.
Okay.
Honestly.
What about neither one sounds fun?
That acetic acid part's kind of intimidating.
Okay, so it has the word acid in it, and so we probably don't want to put our hands into something with the word acid in it. Okay, you want to add to that?
I put B, acetic acid, because its pH is closer to neutral than hydrochloric acid.
What do you mean the pH is closer?
Like, it's closer to 7 than hydrochloric acid. It's closer to neutral. Right?
Okay, so we could do some calculations. Depends on how much we know about acids. So this one, the first instinct I wanted was your gut instinct, what sounds better, and then we can talk about some more of the detailed calculations of why. You want to add to that?
I said B, only because like you can clean with vinegar and you cook with vinegar, so I feel like it's not as bad.
So if we start thinking about why acids are different, if it was me, I would not put my hand in 1 molar HCl. If you leave it for too long, you're going to have chemical burns, your hand is going to be totally messed up, your skin's going to start blistering. If you put it into vinegar, acetic acid, even the stuff that we have at home, it's not 100% acetic acid. It's not 1 molar acetic acid. I think it's about 3% acetic acid or 10%, something like that. So it's mostly diluted out with water, but it's still a lot weaker of an acid than HCl. So today we're going to talk about why that is, what's the difference between different types of acids, and why it is that we have one of them in our stomach to actually help us digest things, HCl, and why acetic acid has a nice smell and we use it for cooking. It still is somewhat of an acid, but it's not nearly as strong as if we were to use HCl. So the big picture that we're going to get at today is this idea that if you put HCl in water, you probably started to see this in lab, that HCl, every single HCl that goes into water is going to separate. It's going to be very similar to an ionic compound. You're going to end up with 2 ions. You're going to end up with every 1 HCl is going to give you 1 H plus ion and 1 Cl minus ion. H plus is a definition of acid. So every time you have an H plus that ends up in water, that is an acid. Any compound that gives you H plus in water is going to be an acid. Question is, how much of it disassociates? If we look at acetic acid, here's the chemical formula for acetic acid, and we're going to start to pay attention to the COOH, or CO2H. Whenever we see that, we know that this is the acidic proton. That's the one that's going to get released. It's going to do something similar, but in this case, instead of 100% of these disassociating into these, so if we have 1,000,000 of these, we're only going to have a fraction of them that disassociate into the H+ ion, which is that acid that's going to destroy your skin. So one of the keys is going to be that those arrows are going to start to tell us a lot about the reaction. And you might have seen this before, but we're going to start to draw equilibrium arrows, where the arrow goes in one direction, so that means that this thing will separate, go over here, but then some of these are going to be strong enough attraction between them that they're going to go back in the other direction. And that's what we call an equilibrium arrow, or an equilibrium reaction. The type of acid on top is what we call a strong acid. The type of acid on the bottom is a weak acid. And I think we're going to circle back around to that once we start doing some calculations and we come back on the back page. We'll go ahead and close that question out. So go ahead and read question number 2. Click in your response. See if we're talking the same language. Once you've submitted your own, go ahead and check the person next to you. Let's do another 15 seconds to submit your response, please. All right, we have 46 responses. Is that everybody? Everybody submitted? Trying to nudge people along. All right. So the majority of our class is pretty confident in this answer. Would anyone like to volunteer what they had? And then we'll kind of talk a little bit about why and when we're going to see this. 1 mole of H+ ions. So what we set up here was that every time every one HCl goes into water and dissolves, we're going to have 1 mole of one H+ ion. So if you have a mole of HCl, you're going to have a mole of H+ ions. So this is going to end up being a conversion factor. So for every 1 mole of HCl, we generate 1 mole of H+ ions. When you're doing your stoichiometry for your titrations lab, this might be a useful conversion factor that you use. And I think we'll use that today. Okay. Would that be the same for, if I go back, would that be the same if I asked that for acetic acid? Let's actually do that as a clicker question. So if I change this to acetic acid, let's do this compound. How would you answer this question? We're talking about acetic acid instead of HCl. So the clicker question on your screen is going to show what I have written up here because I read over it afterwards. All right, let's say we're split on this. Find someone with a different answer than you, around you, and find out why.
Some will break up to be less than other, but some won't. Yeah, it's like salt, like it's really salt.
So you gotta love the clickers. Not sure. Okay, so who wants to argue their case? When you put a mole of acetic acid in water, are we going to have less than a mole, more than a mole of H plus ions that form? Can I get some new voices that we are going to hear in class? Great.
I think it's less than a mole because it's not a 100% dissociation, so you're not going to have all of those hydrogen ions actually associating into the solution.
Great, so up here we were talking about only 5 to 20% of that acidic proton is going to dissociate. That doesn't mean in one molecule 5% of that hydrogen ion releases, because it only can or cannot dissociate. But if we have 100 of them, only 5 to 20 of them will actually end up in the dissociated side on the right side. One of the other things to keep in mind is this is a bit of a sticking point. There's more hydrogens in this molecule, right? Does that mean that it can release more than one proton? For the sake of this class, we're going to say unless it's attached to a COOH, almost for the most part, it's not going to be considered acidic, and acidic protons are the only ones that can release. So these hydrogens here attached to carbon are not polar. You guys remember that term? So non-polar hydrogens aren't acidic. So it's only the ones that are attached to an oxygen typically or a nitrogen that have any chance of being released. And for, I think, the most part in this class, it's going to be if it's a COOH. This is the one that's acidic. That's the one we're going to be paying attention to. So these ones over here don't act as acidic protons. So to answer this question for acetic acid, I would say that it would be between 0 and 1 mole. I think the description was very nice. All right. What's going to really help with this is thinking about when are we going to expect full dissociation of a proton, when are we not? There's 6 strong acids. We just talked about hydrochloric acid. These 6 strong acids, we say when we put them in water, always dissociate 100%. So go ahead and write in the blanks what the formulas for these are. I think with the naming, you should be able to get an idea of what the formulas are. So I'll give you about 1 minute to try to fill in what those formulas are.
I heard it. You heard it right.
How you doing? So for now, just try to fill in these formulas. Nice. I like how you drew the full arrow on the products. So what do you think nitric is? So think about your polyatomic ions. Sulfuric, perchloric, try to think about how those relate to your polyatomics. Let me see what you have. So do you remember, so you know what ACL is, right? Hydrochloric. Try to fill in the rest of these, and then we're going to try to recognize those as often as we can.
I don't want to do it.
This one's tricky. So it sounds like it's
What's sulfate?
nitrite. It's actually nitrate.
What's the charge? That's what I was thinking of.
So remember, there always has to be an acidic proton as well.
-2, right? So how many hydrogens do you need? Right.
And then what's missing? You have so 3 there for nitrate.
Yes, yes.
But it's an acid, it has a proton or a hydrogen. So don't forget your hydrogens. Try that again. All right, let's go ahead and walk through these. Can I get different volunteers for each one of these? New voices? And if you had to Google it, that's fine. Can I hear from the guy in green? Do you want to volunteer one? Anyone, pick one. What did you have for that? Great, and hopefully that one was super easy because you know perchlorate, and perchloric acid is perchlorate with an H plus ion attached to it. So our polyatomic ions are going to come into play here. All right, can I have another volunteer for one of our other strong acids? Yes?
Sulfuric acid, H2SO4.
Great, H2SO4, is this one you're using in lab? No. Okay, great.
Hydrobromic acid is HBr.
Great, and I'm going to put in HCl because we already did hydrochloric acid. Two more. Volunteers? Volunteers? Yes.
Hydronic acid, HI.
Fantastic. And our last one, nitric acid. This name is a little bit tricky. It's actually the polyatomic ion nitrate and an acidic proton, H+. So what is that formula? HNO3. One of the reasons we had you learning polyatomic ions at the beginning of the semester is so that you can start to think about, okay, when you have ClO4 minus perchlorate, it can have an H plus ion, and that's an acid. So you can think about when it goes into water, it's going to disassociate 100% into H plus and perchlorate ions. All right, so we could do this for each one of those. As you notice at the top, we will provide you these on the final exam, or on exam 4. I don't know about, it would be both. The reason is, if you're in general chemistry, you'd have to memorize them, you'd have to work with them a lot. In this class, we don't want to focus as much on that. We want you to just be able to notice that if it is one of these, it's going to fully disassociate. If it's anything with, I believe I have at the bottom of the slide here. Nope, I didn't. Anything with a COOH in it, then that's not going to be 100%. It's not going to give off 1 mole of protons for every 1 mole of that, the weak acid. The bottom here, we said there's also strong bases, which means that every time we put a mole of it into water, we're going to get a mole of hydroxide. So potassium hydroxide would give us K plus ions and OH minus ions in water. The exceptions to that are calcium hydroxide. I can't write. What's wrong about my formula at the bottom here for calcium hydroxide? So what do I need to do to balance this? So a strong base is designated as a group 1 metal, and some of the group 2 metals, calcium is one of those. When it goes into water, all the hydroxides that are with that metal will be released. So anytime we have lithium, potassium, sodium, any of those with hydroxide, that's going to be considered a strong base. And so you've already seen some of these strong neutralization reactions, and this is kind of what we're looking at. So for today's class, by the end of class, I want you to be able to look at a chemical structure and discern what features make it acidic or make it basic. And then I also want you to be able to calculate the pH of a solution given the concentration of H plus ions, OH minus ions, or concentration of a strong base or strong acid, and thinking about that disassociation that we just worked with. Have we been dealing with pH much yet? We heard it mentioned earlier in class. Have you been doing calculations of pH? Okay, you're going to be doing calculations of pH this next week in lab. So let's start working on that. One of the most basic principles of pH, or P anything. In chemistry, there's a lot of P stuffs. Not P like urine, P like the letter P. And so the letter P just means it is the negative log of whatever that thing is that's next. So pH is the negative log of the H plus ions. So pH, that H stands for H plus ion concentration. We've used a lot of concentrations in the last week, though. What kind of concentration do you think we're going to use for the concentration here? Did you have a pre-class primer on this? Okay. So with all of these, it's going to be concentration in molarity. So let's go ahead and do this as a clicker question. And if you can answer this one, then start going down. I want you to write on your paper, though, the work, because we're going to be walking around, me and the LAs and your graduate assistants, and we want to kind of just see how people are writing this out. And if you have any questions on how to do this, please flag one of us down. Do you have a calculator? I guess you could use your phone, right? I find it a lot easier to use a calculator on my phone for logarithms.
So for this one, since you asked me what the POH is, you subtract this from 14. Is it 14 minus 0.7?
So 14 is involved somewhere, but it's involved in the pH, not in the concentration.
So you wouldn't do negative log because you're looking for the solution of the H, right?
You can do negative log of the concentration of hydroxide. You can't do, so negative log gives you the pH. So right here, equals. When you write pH equals.
Yeah.
And
So
then,
if I did negative log of pH here, I'd find the POH and then I'd subtract that from 14. No.
pH plus pH equals 14.
Okay.
Okay, so I don't understand the difference from POH and just regular pH.
Okay, so one is talking about the H plus ion concentration. The other is the OH minus concentration.
So what I saw
Because it's asking for the POH. not the
Yep,
POH.
so work on this one first maybe, and then we'll work on
Well,
that
it's
one
not
together.
asking for the hydroxide.
We have 9 clicks. Are we just not clicking enter answer, or are we not sure how to do this? Yep. Once you put a numeric answer in, always put the numeric answer, send.
So we can't just do
So for the beginning of class today, let's spend some time with working together to see the framework for how we find pH and POH. And then the next two I'm going to let you loose a little bit longer. Does that sound right? It's always nice to have the tools before you're asked to do the work. I don't always do that, but let's try it out. So we just said that pH means negative log, right? That's what that P stands for. And then the H is the concentration of H plus ions. And so this is going to be in concentration molarity of H plus ions. So for this particular example, we do negative log of 0.75 molar. And can I have someone share what they got for their answer? 1, 2, 4, 9. Does that sound about right? I don't think we're going to get into sig figs too much for this class, but for now, add one more sig fig than you think you should for pH. It looks like it should be 2 sig figs, right? Because this is 2. Just add an extra one for this class. So it'd be 0.125 is the pH of the solution. Does that number make sense? How do we check to see if that number makes any sense? Anybody? We just like plug in a number, we're good, let's go. That always works well. So how do we know if the number makes sense? Anybody? Can I get some great insight, maybe from the back corner of the room? Yeah. You raising your hand? The blue shirt? Anybody want to help? Okay, I'll start with this one. Hopefully for the next one you guys will be able to tell me. Does this seem like it would be an acidic solution? Is 0.75 molar of H plus ions seem concentrated?
Yeah, because it's supposed to be.
So there is more than 0 of H plus ions. There's actually a decent amount of it. This is similar to what you have in lab in those little bottles. I think those are 1 molar HCl. Is that right? And you put that stuff on your skin for too long, it's going to burn. So it's acidic. What pH is acidic? Anything below 7. So pH equals 7.00 is neutral. Anything higher than that is basic. Anything lower than that is acidic. We have an acidic solution. We have H plus ions in it, a lot of them. So we're going to expect a value less than 7. That's good enough for me today. So then the next question is, if we know the pH is 0.125, what is the pOH of that solution? And to answer this question, we're not going to get too much into all the math behind it, but the big takeaway is that your pH plus your pOH is always equal to 14. So pOH stands for the negative log of the concentration of hydroxide ions in water. So go ahead and click in what the pOH of the solution is. This is the same solution we were just working with. Take about 30 more seconds to continue your response, please.
Not 0.75, that's your like molar concentration. You use that to find your pH. What did you find?
Okay, I'm looking at all the responses as they come in. Can I have a volunteer to describe just really briefly their calculation and what value they got? Can I have a new voice? Yes, please. 13 point? How'd you get that? You're close. You're very close, but I think you might have missed a digit. Can you just tell me how? Tell us how, and then I think we'll get to it.
I subtracted 0.125 from 14.
So I think you might have subtracted 0.25 from 14. You might have missed that first one. Close, very close. So right, so that's 13 point.
No. It's not.
Okay. And maybe I always hate sig figs with logarithms because they're such a pain. So the number of significant digits is, because the adding one doesn't work when you're doing this, it's however many digits past the decimal. So this way I have it written right here is actually 3 significant figures in logarithms, which is pH and POH. Can you remember that?
So it's the sig fig after the decimal.
Exactly. So however many digits you have past the decimal they're all significant digits. So this is 3 significant digits the way I have it written out. The reason is it's really about exponents. Logarithms are all about exponents. 10 to the what? This is 10 to the negative 13, really. So this just tells you how big or small the number is, and then this actually tells you how significant it is. So this is how we would find the pOH. What if instead we have the concentration of OH minus? I think that's our next question. Can you all figure out how to do that? How to find the pOH and pOH? pH and pOH? So now we have a solution where we know exactly what the concentration of OH minus is. This is question number, 5 or something? Question number 5. Go ahead and calculate and submit your answer for what the pOH of this solution would be. And if you're stuck, please wave one of us down.
We gotta break that down. Okay, now you just say it.
I'm just literally reading the question. It says, what is the pOH? 12.269.
Okay.
So they just gave you the concentration of OH minus. No, these are 2 different solutions. Yeah, so these are 2 different solutions. This solution is a solution of H plus, and this one is a solution of H.
So it's really important. For this one, this is going to be the
I'm
direction.
trying to see how you're thinking about it. In regards to the question, this is
All right, how do we set this one up? How do we find the pOH for this solution? Notice I didn't ask for pH first, but we'll see how we can find that. Can I have a new volunteer? How do we find the pOH for this solution? Yes?
So first you have to find the pH, right?
You can't. Well, in a roundabout way, if you spend a lot of time with pH and pOH, you might be able to. But in this case, we're going to go directly to it. How do we do that? Yes? Negative log. Keep going. Okay, so what we're saying is we're doing P of the OH minus concentration. pOH. So that is pOH. And what value did you get when you calculated that? How many sig figs should we have here? We should have 1, 2, 3. We're only showing 2 past the decimal. Give me one more. 5? 1. So the pOH of this solution, is that right?
0.
Okay, I probably should have calculated this myself. I'm lazy. It's, so right now, past the decimal, there's 1, 2, 3. This is the logarithmic value because it has the P. This is not logarithmic. This is just a concentration. So this one has 1, 2, 3 significant figures, regular rules, just like we've been doing. But as soon as you take the log of something, then we have these special rules with just the digits past the decimal. I know, super annoying. Sorry. I don't think we're going to grade very harshly on the exam, next 2 exams, based on sig figs. But I at least wanted to give you some idea that if you're like 13.1 is 3 sig figs, it's not. So we try to include a decent amount past the decimal. That's the most important thing. Okay, so we found the pOH. Great. Now do we know how to find the pH? So go ahead and do that. I'm going to close that out. I'm going to do the next question. Go ahead and find the pH of this same solution. Both of them are negative log. Because remember, negative log means so if it's pOH, and then they're related to each other by the 14. So they both have to add up to 14 for any something. So that's why this plus this equals 14. That's why this plus this should equal 14. So can you write out pOH equals? So you're saying it's 1? Because the formula is identical, so you can make sure that you're all right, let's do 30 more seconds for this.
So your pH is the measure of your hydrogen, like your H plus concentration. Your pOH is the measure of your OH concentration. So you have to look at it. But this concentration is OH. So if you're negative log of that, you're going to get OH. Because that's the concentration, right? So if you want to find the pH, you're going to take the 14 minus your pOH to get the pH because the corresponding. The 14 is equal to pOH plus 1. Does that make sense? So just look at what concentration you have, and then log that with whatever the concentration is.
Okay, can I have a volunteer to help us describe how we found pH of this solution? A new volunteer. I want to try to hear from as many voices today as we can. Yes?
You did 14 minus your pOH, which was 1.571. And I got 12.43.
12 point.
4 thirds.
Give me one more digit.
They didn't give me any.
So it'd be a 0 probably? Okay. Fantastic. So what we're trying to look at is if we have a concentration of OH minus or H plus, we can find the negative log of that, and it's either the POH if it's OH minus concentration, or pH if it's H plus ion concentration. We only need one of them to find the pH and the POH because they're related through that 14 number. So we're going to take that and start applying it to solutions that I'm not just telling you the ion concentration. We're telling you the concentration of strong acid or strong base. Any questions so far on finding pH, POH with what we've done? You can always ask as we're coming around. And that's not very useful. So let's talk about the pH of a solution of this particular compound. And what I want you to do is, as you're thinking about how to calculate the pH of this solution, write out anything that might be implied in your thought process. You might say, oh, I know this, that you do this and this. Write that out so when we walk around we can kind of see what people are thinking. It helps me guide the discussion in a few minutes. Question number 7 on your worksheet.
I got you.
That's why you put these. We get the RV. No.
Well, you can't get a negative. There is a way. I've done this before. I can't remember what I did. There's a way we can cancel out negatives.
So are they. That's okay. So that's a super, really concentrated. You really shouldn't at 0 to 14, but it's really, really concentrated. That's the correct way. That's what you'll get. When you do your calculator, maybe let's find this a different way. I would say just yeah. And I'll just go to the tutor while we talk in there.
It's all about trying to find what you can and then figuring out what. Got 29 responses. Let's get 30 more seconds to submit your response. All right, we have 43 in. I'm going to write what I saw in a lot of papers, and you can tell me whether you agree or disagree. So we're going to say, well, I have a molarity, I want pH, and I know that P is a negative log, right? So I'm going to say that the pH equals negative log of 1.25 molarity. Sound good? You're shaking your head in the back. Do you mind explaining why you're shaking your head? You don't have to. You can pass if you want. Can someone explain what I'm doing wrong?
You didn't see how many hydrogen ions.
Great. So pH is specifically the concentration of H plus ions in the form of concentration molarity. HBr is not H plus ions, but they're related, right? How are they related?
They disassociate completely.
So we had this formula before where we said that HBr would disassociate fully into H plus Br minus ions. Remember that? 100% disassociation. So that's conversion factor. So we could say that we have 1.25 moles of HBr per 1 liter of solution. Right, that's what that big M stands for. Molarity is 1.25 moles of HBr in every 1 liter of solution. But I'm going to use a conversion factor to convert that into something I can use for pH. So for every 1 mole of HBr, what do I put on the top of this conversion factor? 1 mole of H plus ions. So what we find from that is we actually do have 1.25 moles of H plus ions in every 1 liter of solution. So that means we do have 1.25 molar H plus ions. What you're going to get yourself in trouble with is if you don't think about how many H plus ions you have, then you're just going to use a concentration that's not actually the H plus ions. So in the end, this calculation gives you the correct value, but I want you to be very careful about why you're using 1.25 molar, because it's 1.25 molar of H plus ions and not just of the HBr. So then our pH ends up being, can I have a volunteer for the actual number, numeric answer? 0969. Is it negative or is it not negative? Can you have a pH that's negative?
No.
Yes.
What?
What? It is negative. So here's what's crazy, is if, and for a point of reference, so always trust your calculator when you're doing this, make sure it makes sense. But a pH of 0 is a 1 molar H plus ion concentration. So pH equals 0 is 1 molar H plus ion concentration. If you have anything that's stronger than 1 molar H plus ion, it's actually going to be a negative value. So that is completely possible. Let's really briefly do 9, 10, 11, 12. They're just definitions. I just want you to have the definitions when you're going to lab, okay? So let's look at... I've been throwing this term out all day, and hopefully you're starting to get used to it. An H plus ion, we call it a proton. Do you know why?
Positive.
It's positively charged, and if we have a regular hydrogen, that's defined as 1 proton, right? Atomic number of 1, and 1 electron. If we have an H plus ion, it has 1 fewer electrons, and so that's only 1 proton, and that's it. So as chemists, we simplify and we say, well, this is a proton, because literally that's all it is a proton. So that's some terminology that's going to be useful. We've been talking about definitions of acids and bases. So anything that gives up a proton, that donates a proton, is an acid. Anything that will take in a proton, like an OH minus, that's our definition of a base. And we've already talked about our definition of strong and weak. And then here's your 2 giveaways for what is going to be signs of a weak acid. It's anything with that COOH attached to the rest of the molecule. And things that are going to accept a base some of the time are going to be things with a nitrogen that has a lone pair on it. You notice how I add that lone pair there on that nitrogen? So you might see that in your class or in your homework, that a nitrogen with a lone pair can act as a base because it can accept a proton with that lone pair. All right, we got through about half, 2/3 of what I wanted today. It's very nice meeting you all. Good luck in the rest of the semester.